A second one is the last method. So this is my last method, is based on the maximization of the total likelihood. Okay. So if you remember our nonlinear state space model, so the first equation, I put it in the second slide or third slide. So here the objective is to try to maximize this function. So this function is taking into account first the dynamic of the system. So it's the product of all the PDF of x at time k, knowing the past. So here we apply the model basically, and it is depending on the error of my model. And here, this is the PDF of my observation equation. Okay, so it's y given x, and the noise in this equation. So basically, the likelihood function is taking into account these two matrices or two parametrization of these matrices, and we want to maximize this likelihood. We have also the initial condition, which can be very important in some of the problem. So I didn't talk about this here, but we can also include the initial condition in the likelihood function, and sometimes it's very useful. So this technique in state space model is very old, I will say. It was given by Shumway in the 80s for the linear and Gaussian case. So this is very famous for this case. So in our case, we are in a nonlinear and Gaussian, and you have these three main papers dealing with nonlinearity with chaotic model. Try to estimate Q and R when we use a chaotic dynamic. And so there are different algorithms to solve this problem. So if you are a statistician or mathematician, you know so you can use a direct optimization of this function. Okay, so it's based on Cassey-Newton algorithm. You can also use, for instance, grid-based algorithm. So you choose different value of Q and R, and you launch the computation of the likelihood for these different points, and you evaluate what is the best parametrization, let's say, based on the likelihood criteria. But I think the best one and the more efficient one is, in practice, to use the expectation maximization algorithm. So this is very famous also in the statistical community. So I will not go into the details, but it's quite simple. It's an iterative algorithm. So basically, you have to put a Q and R initial condition, and then we compute an expectation of this likelihood function. So we use a Q and R. We launch the Kalman filter and Kalman smoother, and we are able to compute the expectation of that. And then we use what we call the maximization step. And in this case, we have an analytic form for the Q and R matrices. So at each iteration, we update the Q and R matrices, and it is quite robust in practice. And I think this method is for what I've tested all the method, and I think this one is very relevant in data assimilation. Okay, so now it's finished with the equation. So I would like to show you different example application in simple cases. So in the different application, I will show you they are based on these techniques, okay? So on using the EM algorithm to find Q and R. So this is a first example to show you in a very simple univariate problem. This is wind speed in my hometown in Brest in Brittany. So we have a lot of winds here. It's in January. It's very windy, and this is a very simple time series, and we want to we want to use a dynamical model, an autoregressive order 1 model to model this time series. So maybe a simple R1 model is maybe too simple, but we try with this simple model. Okay, so we assume that the dynamic is given by that, and we want to know the error of this simple statistical model, and also the error of the instrument that measures the wind speed. So I apply the EM algorithm. So you see here the iteration of the algorithm. So basically, we reach to something. We don't know exactly if it's the maximum likelihood, but we are going to a local or global maximum. And here is the estimation of the error of my simple model, and here the estimation of the instrument noise. Okay, and so first I will discuss about this. So I don't show here, but the instrument noise, we talk with the people who we buy the instrument, and in the instrument they say that the level noise is very close to 0.2. So we are happy with that, because our model is able to estimate more or less the good error. Here is the error of my autoregressive model. Okay, so what I will say is that we can use, for instance, a more complicated model here, in a more complicated, for instance, statistical model. And what is nice is that if you estimate Q and R adaptively, if you change that, it will change the Q estimates. And in practice, it gives some good results. Okay, so now I move to. Yeah, of course.
So your Q estimate goes in the wrong direction for percentage recovery.
Yes, and this is.
Does that worry you?
Yes, yeah, it worries me a little, and I talked to all the people who are applying EM algorithm in nonlinear state space model, and it seems that it's very common to have this kind of behavior, and we are still working on that, trying to see what is going on. If
interpret it as like you need to estimate R well enough first before the Q estimates are headed in the right direction.
So you suggest to estimate R first?
No, I'm just trying to explain the behavior.
Okay. Honestly, we are still looking on that, and I agree with you.
The log likelihood is increasing monotonically.
Yes, yeah,
so
completely.
It makes it seem like the R estimate is the biggest contributor. The error in the R estimate is the biggest contributor at the beginning.
Yeah.
And then the Q estimate.
And yeah, maybe. Yeah. So I think people here have maybe a lot of experience, know very well the EM algorithm, and we can talk about this maybe after. But you are right, it's worrying me a little. Yeah. So this is I move to the 2D example. So so now it's I'm working with satellite images. So this was part of my thesis. During my thesis, I used satellite infrared images to measure the temperature. And so you can see that most of the time we have observation and sometimes no. So this is due to clouds, to the presence of clouds. So basically the satellite is measuring the temperature of the cloud, and we are interested in the temperature of the sea, so we remove this information. And we have this kind of maps, and we want to interpolate the maps. So basically, we are doing statistical methods we are using spatial and temporal interpolators to get a good estimate of the sea surface temperature. And then this temperature is used in oceanographic model or also in meteorology. Okay. So here I use a large database of 40 years of images. So every day I have this kind of map. So it's daily map, and the resolution is close to 5 kilometers. So here I'm not using anymore temporal autoregressive process. So now I'm using a spatio-temporal autoregressive. So I will not go into the details of this model. It is what it is. But we try to estimate for all the pixels. We try to estimate basically the spatial and temporal correlation length. So I will not go into the details of that. What is interesting is, and the focus of this presentation is, how good is my model? So this is the error of my simple statistical model, and how good are my observation, satellite observation. So first, my model. So you see that we have strong errors in these places. So this is a expected result, I will say, because here I'm using a spatial autoregressive process. So I'm using only temperature data, and in this place, if you know this part of France, it's a very windy place, and we have a strong link between the wind and the sea surface temperature. So basically, when the temperature is increasing, you have some wind, and then the temperature is decreasing very rapidly. So in my very simple model, I don't use wind, so that's why I have strong errors in my model. So this was expected. This is also the case in Norway and in this part of Europe. So basically, there are very strong winds and winds in the fjords that produce this kind of error. So basically, my statistical model is not able to get the good dynamics, but we are able to estimate, to know that there is an error. So this is nice, because we know that the model is not good, but we can put a given error to these places. What also, so now I move to the satellite error. So this is also known, I think. So this is the global mean of the diagonal terms of my R estimates. So this is only the diagonal terms. And you see that there are strong errors in this part of Europe. So basically, I think it's due to the presence of ice in the ocean. So this is also well known for people working on remote sensing. They know that when there is ice or very cold water, the inversion algorithm of SST is quite bad. So this is a good indicator, I will say, to the producers of remote sensing data, because with this technique they will be able to know where are the errors of the SST measurement in this case.